Hello everyone, welcome to this video series on cryptography and network security lab. So today we are going to look at program 11. So like and share the video and also subscribe to my YouTube channel for notifications on latest videos. So what is the aim of program 11 is, it is to implement Diffie-Hellman key exchange algorithm, and they are asking us to implement it using HTML and JavaScript. Okay. So I would like to mention one thing. This is not actually a key exchange. It is actually key generation algorithm. Okay, so actually the generated key is never exchanged between the two parties. It is just created and used. That's all. Okay. So you see the process and you will understand why I'm saying like this. So what is the key exchange problem? So all of you know about this symmetric encryption, right? So in symmetric encryption, the same key, that is the secret key, is used by both sender and receiver. Okay, so what is the bad thing here is, so the sender and receiver must somehow share this key, okay, before actually starting the communication. So if they share the key, it will be in plain text, right? So if it is plain text, the hacker can see it. If the hacker can see the secret key, then there is no use of encryption and decryption, okay, because the hacker can decrypt whatever encrypted text passes through. Okay, so this is the key exchange problem. How does sender and receiver share the secret key with each other? Okay, so the solution to that problem is the Diffie-Hellman algorithm. So there are two people. Diffie is one person and a Hellman is one person. So this is the process. So you have two entities, Alice and Bob, okay, who want to communicate, and there is the third person, the hacker or attacker called Charlie. Okay, right. Now initially, what I want to say is this works on like public key cryptography. Okay, so you know what is public key cryptography, right? There are two keys. One is private key, okay, and another one is public key. Okay, so Alice has two keys and Bob has two keys. So how these keys are used for generating the shared key, you will see in the process. Okay. Now first, before doing anything, Alice and Bob will agree on two entities called P and G. So P must be a prime number. Okay. In fact, it should be a very large prime number. By large, I mean it should be 1024 bits or 2048 bits. That big. It must be that big prime number. Okay, and G is a primitive root modulo of P. Okay, and G is another number which is a primitive root modulo of P. Okay, so I am not going into details what is meant by primitive root modulo P and all those things. If you are interested, you can check in Google what is meant by a primitive root. All right. So these two things, that is P and G, they are known to the third person Charlie also. So Alice knows P and G, Bob knows P and G, and Charlie also knows P and G. Now next step is Alice will generate her own private key and Bob will generate his own private key. Okay? By private I mean only Alice knows what is this private key A and only Bob knows what is this private key B. Charlie doesn't know what is this private key A and private key B. They are secret. Okay. Now next step is using this A, P, and G. Alice will compute capital A, which is the public key of Alice, and the formula used is this G power A mod P. Okay, so this capital A is the public key of Alice. Similarly, Bob also generates his own public key by using this formula G power B mod P. Okay, now A will send this public key to B, and Bob sends his own public key B to Alice. They exchange with each other the public keys. Okay. Remember that the private keys small a and small b are never exchanged. They are kept with Alice and Bob themselves. Right? Now, what does Charlie know? Charlie knows P. Charlie knows G. Charlie also knows capital A, and Charlie also knows capital B. Okay. He knows all these things. The only things that Charlie doesn't know is small a and small b. Right. Now, once Alice and Bob exchange their public keys, Alice will compute the shared key using this formula: B power, capital B power, small a mod P. So, what is this capital B here? It is the public key of Bob which he sent earlier. Similarly, B also will generate the shared key by using the formula capital A power small b mod P. Okay, capital A is the public key which is sent by Alice. Right. Now, if you check out this capital S, which is generated by Alice and also which is generated by Bob, they are same, and that is the shared secret S. Okay. Now this S is never exchanged between A and B. Okay, A has generated S and B has generated S. They didn't communicate, but still they are the same. So this is the beauty of Diffie-Hellman key exchange process. Now, what is the difficulty here for Charlie is, so let's say Charlie knows A, right? Capital A, which is computed using G power A mod P, right? Okay, so Charlie knows this. Charlie knows G and Charlie knows P. So the only thing Charlie doesn't know in this is small a, which is the private key of Alice. Now, even if Charlie tries to brute force the value of small a, it is not possible. It is impractical. Okay, it takes very long time. By that time, Charlie might be dead also. Okay, why? Because I told you at the beginning that the value of p is very large, right? So it is impossible to brute force the values of this small a and small b. Okay, and let me show you something that is happening here at this step. So this capital S is equal to b power a mod uh, p. So what is this b? B is this, right? So Bob will send the b, right? So let's substitute the value of b here. So it is g power b mod p. So this is the value of b, and here you have a mod p. Okay, so by modular arithmetic, this is equal to g power ab mod p. Okay, so on the Bob side also you will get the same thing like this. So that's why the value of s is same on both Alice and Bob. Okay, so this is the Diffie-Hellman key exchange process. So I told you it is not actually key exchange; it is key generation, right? So the actual shared key is never exchanged between both of them. It is generated, right? Okay. So the same thing which was represented in the diagram, it is in the form of text. So let me go through this quickly. So both parties, Alice and Bob, they agree upon two values. One is P, which is a large prime number, and another uh, number which is G. So G is a primitive root modulo P. So if you are interested in knowing what is primitive root, please check in Google. And as I told you, P and G are not secret. Everybody knows about the value of P and G. And G can be a small number, but P, it must be a very big number. Okay, so it should be 2048 bits or even 4096 bits long. So that size is very big. Okay. Now, second step, that is after generating P and G, is both Alice and Bob will select their own random private integers, that is small a and small b. Okay. The thing is, small a and small b are kept secret. They are never shared with each other. Okay. No one knows about a and b, small a and small b, except Alice and Bob. Now, Alice calculates public key capital A using this formula and sends it to Bob. And similarly, Bob calculates his own private public key capital B using this formula and sends that to Alice. Now, Alice will calculate the shared key using this formula. Okay, and Bob will also generate or calculate shared key using this formula. So if you see here, both are same, right? So this is how the shared key is generated. So example, here p value is 5 and g value is 2. So in fact, in reality, the p value will be very, very, very big, but for demonstration or for understanding, the values are chosen very small. Okay, and Alice private key is selected as 6, and Bob's private key is 4. Now Alice is calculating her own public key using this formula, so values are substituted, and the result is 4. Similarly, B is calculating his own public key using the formula, values are substituted, and the value of public key of B is 1. Okay. Now Alice and Bob will exchange their public keys, and Alice receives B's value and Bob receives Alice's value. Now Alice calculates her shared secret key using the formula. So values are substituted. So final value shared key is 1. Similarly, Bob calculates the shared key. Okay, values are substituted, and the value generated is 1. So if you see here, the shared key is same, right? Now using this shared key, Alice and Bob will use symmetric encryption. Okay, so one is the shared secret key. So this is another example. P value is 23, G is 5, and the secret key of Alice is 6. Secret key of, I mean, private key of Alice is 6. Private key of Bob is 15, and public key of Alice is 8, and public key of Bob is 90. So using all these things, the shared secret value generated is 2. Okay, right. Now that's it about Diffie-Hellman key exchange algorithm. Hope you have all understood it. Thank you.